Manu,
Yep.
is the stream going on? Like, is YouTube running already?
Yep. YouTube, it's done. And as soon as you say we start, we will restart the recording.
Okay, maybe you can start recording and I'll start speaking.
Okay.
So, Jim, just let me know whenever you're ready. I'm just gonna address the audience real quick in Spanish, and I'll be back.
Sounds good.
Okay, thanks. Okay, bienvenidos a todos los que están aquí presentes a este coloquio que hemos organizado como parte del Bootcamp que estamos realizando. Y solo para aclarar, tenemos un invitado especial que va a estar dando nuestra presentación del día, pero es una persona que obviamente habla solo inglés, y les quiero hacer saber a los asistentes que el coloquio va a ser en inglés. Y bueno, de aquí en adelante voy a cambiar a inglés para que Jim nos pueda escuchar y nos pueda entender, y bueno, espero que sea el agrado de todos. Así que cambiate ahorita. So, well, welcome everybody to this special colloquium that we organized for the ICTP Physics Without Frontiers Physics REBoot Venezuela Bootcamp #1, which is kind of like a mouthful to say, but I went through it. So we have a very special guest from like Jim Halverson from Northeastern University. He's an associate professor at the Department of Physics at Northeastern University, and he's also affiliated to the NSF AI Institute for Artificial Intelligence and Fundamental Interactions. And well, he has a very thrilling topic to discuss today, and I hope you guys enjoy the presentation. But before we start, I just wanted to let all of you guys know that if you have any questions, just either if you're here on Zoom, just unmute yourself and let Jim know any questions you have, or just write it in the chat, and I'll basically let Jim know that there's questions. For the folks that are following us on YouTube or any other platform where the stream is happening, just feel free to use the chat in those platforms, and I'll try to communicate the question again as well with Jim. So I think that's it. I'll leave the floor open to the very capable Jim Halverson. So Jim, go on.
Hello, everyone. It is great to see you virtually. Thank you very much for coming to my colloquium and for your interest in this work. I'm sorry that I'm not able to speak to you in Spanish. I wish I could, but I simply can't. So maybe someday, but I hope that the speaking in English is okay. Today, I'm going to tell you about connections between physics and math and computer science that presents an optimistic view of not only what is happening in deep learning and in machine learning, but also how it's related to math and physics. And I'll have two examples that I'll discuss. One having connections to knot theory, and another having connections between neural networks and quantum field theory. I understand you're coming from broad backgrounds, so I'll try to keep some aspects of the technicalities to a minimum, unless it's something that people from broad backgrounds know. But I'm really excited to tell you about this, and so without further ado, let me take it away. So first of all, if you're interested in this area, there are 3 good ways that I know of, and there's far more also, to connect at the interface of physics and machine learning. First of all, I am thrilled to be a part of this Institute for Artificial Intelligence and Fundamental Interactions, also known as IFI. This is one of 5 new NSF institutes funded by the National Science Foundation, and this is the one at the interface with physics. If you're interested, we have colloquia beginning next week in this area, and we're interested in ways in which machine learning can help physics and math, and also ways in which physics and math can help machine learning. Second of all, I'm one of the co-organizers of Physics Meets ML, which is a virtual seminar series with people from industry and academia. physicists, computer scientists, whole range of backgrounds here. This is a great way to connect virtually as well. And finally, if you want, feel free to contact me. I hope that you'll feel free to do that if you want. So I'll begin with a little bit of a review of some of the things that have been happening in deep learning in the last 10 years. And what I want to emphasize to begin with is that deep learning is not one thing. So if you've heard about deep learning, you may be familiar with what is called supervised learning, which is the idea that in this data set where each image, each handwritten digit is a different data point, you want a computer program to be able to teach itself to predict 3 when it sees that, or when it sees that, or when it sees that, or when it sees that, because they're all 3s. On the other hand, if it sees this, it had better not predict 3, it had better predict 9. And this is the sort of thing that you might have heard of as the most famous use case for deep learning, which is called supervised learning. The idea is, given some input, predict what the output is, and to then test it on unseen data and see how it does on data that it hasn't seen during the training process. There's something called a deep neural network that I'll talk about later in the talk that is central here. But this is the basic idea, to predict outputs given inputs. On the other hand, maybe you have watched the movie AlphaGo, which previously was on Netflix and is now on YouTube. AlphaGo is a nice movie, which I highly recommend, about how Google DeepMind used something called reinforcement learning to beat the world champion in Go, which is a famous board game. I'm more familiar with chess, so I've emphasized the chess aspect here. And basically, the idea is not just to predict outputs given inputs, but instead to imagine that there's a little computer agent that can explore a space of states according to some policy function that tells it how to act given a particular state. So the idea is that by successively following that by following that policy successively, by taking a state and then having an action come out of it according to the policy, taking the action, ending up in a new state, etc., you have a way to follow a trajectory through state space, also known as playing a game. So this is where DeepMind has such famous results. Of course, reinforcement learning is a whole field in machine learning. And this sort of intelligent exploration of state space, it seems like a fundamentally different use case than the supervised learning that I mentioned a moment ago. On the other hand, there's something called generative models, which is yet another use case for deep learning. On the right here, we have 2 pictures. And these are 2 pictures of, if I asked you, are these humans or cats? You would say they are humans. But then I would say, okay, what does it mean to be a human? In this case, these are images that look like images of humans, but normal images of humans are images of people that existed at some point in time on planet Earth. These people simply do not exist. These are people that were generated, these are images of people that are not of real people, that were generated by a neural network. And the basic idea is to learn to simulate something you care about. That's what generative models do. They generate fakes of data that you care about. For various reasons, one cares about pictures of humans, and so you might want to generate a fake. The basic idea is the neural network learns to map some noise distribution, some draw n from some noise distribution, P of n, to some target data distribution. And this has applications in physics as well. I am not going to cover those today, but I wanted to mention it. This is a third use case. So supervised learning, predict outputs given inputs. Reinforcement learning is in a sense about gameplay, intelligent agents that follow trajectories through state space. This is about generative models that literally take noise and generate data that you care about, in this case, images. And the point is that neural networks are central to all of these use cases. In the case of supervised learning, the neural network is a powerful function that predicts outputs, for example, class labels given an input. In generative models, the neural network is a powerful function that maps draws from a noise distribution to draws from a data distribution. And in reinforcement learning, the neural network is a powerful function that, for instance, picks intelligent state-dependent actions. And I'll talk about this example at length. So this looks like a knot, right? And given a knot, you know from untangling your headphones, if you don't have AirPods, if you have the ones that actually have the cords, you know from untangling them that there's a question of how hard it is to untangle them. And there's a question in knot theory, which is a fundamental one, which is, can you even untangle it? And if I just hand you this and I say, can this be untangled or not, in principle, without serious work, you can't answer that question just by staring at it. And I'll show you examples that are easier later. And so what are we to make of all of this progress? We're seeing new directions, and there's a question of how it fits in with the way we normally think about the natural sciences generally, and also physics specifically. There are these breakthroughs in computer science. You know, what is happening broadly in this area, and how should it fit in? And so I want to emphasize what I view as the usual story in my field, which is I'm a string theorist by training. And that's that math and physics belong together. This is not, of course, unique to string theory. Math and physics belong together in a great deal of generality. It caused Eugene Wigner to speculate and wonder about, you know, why is it that math is so good at explaining things in the natural sciences? And, you know, if I have a little math node and a physics node, I can talk about the ways in which math influences physics via these techniques, calculus, which you all know, and other ways in which physics, Newtonian mechanics, of course, but also things like Chern-Simons observables for knot invariance, with ways that physics influences math. And so we're very used to this interplay between math and physics. It goes back to the Greeks, right? On the other hand, computer science is young. In the 1800s, Lovelace and Babbage laid the foundations of computer science. In the 1940s and 50s, Turing et al. Developed a theory of computation, and there's major experimental breakthroughs. In the 1980s, personal computers start to take over. This is an age of accessibility where normal people like you and me, for the first time, can start to get access to computers. We don't have to be a part of a national lab to be able to do that. In the 1990s and early 2000s, the internet and its power grew, and the power of computers grew. I remember when the internet started to become popular in 1994. I was 10 years old, and I learned about something called a web browser, right? So this is all pretty recent stuff. In the 2010s, we saw breakthroughs in deep learning, which is this big subject in computer science that is sometimes called machine learning or also artificial intelligence. And, you know, in the 2020s, we're, I guess, 2 years in now, or a year and a half in, there's a question of what we'll discover in the next 10 years. But the point is that computer science is very young. And if you're interested in this history, I highly recommend this book by Walter Isaacson, about the innovators, how a group of hackers, geniuses, and geeks created the digital revolution. I also highly recommend his book on Steve Jobs and also on Albert Einstein. So the point is, computer science is an infant. This is not an insult. It is exciting. When there's a new field that is developing that shows a lot of promise, we should get excited about that. It means that there's a lot to do. And so I'm interested in this question that I think there's an obvious answer to, which is, what will people say about this first 200-year period of computer science in 500 or 1,000 years? How will it fit in? And what I think is clear is that this relationship that I talked about between math and physics that goes back to the Greeks that we all know so much about, computer science can't have that relationship with them yet because it's just too young. What I think we're starting to see is ways in which computer science can influence math back and forth, and computer science can influence physics back and forth in the same way that math and physics influence each other back and forth. To me, it seems inevitable that this is where things are going in the coming decades, centuries, et cetera. Computers are central. It's not just about deep learning. It's also about quantum computing, which will eventually be a reality. And that's something that is already starting to happen in the string theory community. So, you know, are we moving towards a triangle of influence is the question. This is one way to phrase what we're doing at the NSF AI Institute for Artificial Intelligence and Fundamental Interactions. We want to really try to do everything that we can to make these connections as strong as possible, because we think that the promising things that are happening in computer science itself have a lot of ways that they can help us in physics. And what I'll hopefully convince you of today is that even physics can help computer science. These are overlaps between large and diverse fields. I can only give you a glimpse of some of the possibilities, and that's what I'm going to do. So the outline of this talk is to tell you about 2 lines of the triangle. The first involves ways in which machine learning can be applied to math. In particular, knot theory is a beautiful subject in topology. I will introduce it. If you haven't heard about it, don't worry. It is a deep subject, but it's one that's actually fairly easy to explain. And I'll ask the question, can machine learning help us to unknot complicated looking knot diagrams? This is remarkably similar to natural language in ways that I'll talk about. And second of all, I want to ask, can physics influence machine learning itself? So neural networks are surprisingly like quantum field theory. And there's a question of whether techniques from the latter can help us understand the former. So that's the outline of my talk. And this is a good time to pause to see if there are any questions. Okay.
I think YouTube it's fine.
Okay, great. So the first example is applying machine learning to math. This is based on a paper with some friends of mine called Learning to Unknot. This actually isn't to appear anymore. This is published in Machine Learning, Science and Technology. And I'd like to tell you about it. So the outline of this section is, first of all, to tell you a little bit about knot theory itself. This will be the main section that I'll talk about probably, this example. I'll tell you about the unknot problem, and I'll tell you about decisions related to the unknot problem, including a particular type of architecture called reformers and something that I would say involves hard knots. And then I'll talk about solving the unknotting problem with reinforcement learning. So knots and natural language, why are these two things related? So first I need to tell you about knots. This is a knot. You can see it, that's a knot. If you take the knot and you cut it, you could cut it along this axis right here, and then you would have sort of two sets of endpoints. You could take them and you could stretch that knot out after you cut it, and it would look something like this, yeah? And we can see that there are these different moves that are happening in this object that is called a braid. Actually, there's only one move repeated multiple times, but there are multiple types of moves. You could have this strand go over the other one. That's actually what happens here 3 times in a row. Over this top strand goes over the bottom strand, top strand goes over the bottom strand, top strand goes over the bottom strand. And I will represent that by sigma 1, sigma 1, sigma 1. Alternatively, if the bottom strand went over the top strand, I would write down sigma 1 inverse, because these operations undo each other. So sigma 1 and sigma 1 inverse are opposite operations that cancel each other out. But then I can, once I have this representation, I can just drop the braid picture entirely and represent this knot by sigma 1, sigma 1, sigma 1. Or alternatively, I can drop the sigmas and just represent this knot by 1, 1, 1, where the meaning of the ones is associated with the braid that I get from cutting the knot, etc. So this is a way to represent the information in a knot by a sequence of integers that encodes the information in a particular way. I should also say that given any braid, you can pass back to the knot by doing what's called taking the closure, which involves connecting the endpoints around like that, and then connecting the endpoints around like this. So you can see if I connect the endpoints in that way, it takes the braid and it turns it back into a closed object, a knot. There's a group structure associated with this. The group structure involves this inverse operation that I already told you. So you can see how if I take this one, sigma 1 inverse, bottom over top, and then I do top over bottom, if I do this operation after this operation, what I could do is undo those, pull them past each other, and turn it back into this, which is the identity. So this has the structure of, well, that's one aspect of why it has a structure like a group. The other thing that you can do is compose the operations. You can take this operation on this 3-strand braid and this operation on this 3-strand braid and glue them together into this operation on this 3-strand braid. The operation is also associative. This forms what's called the R10 braid group. There's also notions of equivalence between braids according to braid relations. you can see in this case that if I take this and slide this one forward and this one back, that I end up with a picture like this. And topologically speaking, I did this without ripping or tearing. So these are topologically equivalent knots, topologically equivalent braids. And there's a second relation as well. So there are these relations between different looking braids under which they are actually topologically equivalent, and they are relations associated to the particular braid representative. This is called the braid word. So this braid is represented by 1, 3, 2. There's another type of equivalence that is worth mentioning. I will explain the simplest one. You can see how if I do this operation of taking the closure by connecting that and that, this and this, and this and this, and this and this down here, if I take the closure of this object, you can see that this last little bit that I included at the end, in the closure, when I take the closure, I can get rid of it very easily because this loop closes below, and all I have to do is untwist it, and I get rid of it. So that gives that, what that means is that the closure of this braid here is topologically equivalent to the closure of the total braid just via untwisting. So there are also moves that preserve the topology of the knot itself while changing the braid. If this is getting a little complicated, the upshot is that you should, when you think of knots as braids, they are represented by words, and knot equivalence, the topological equivalence of two different knots in the language of braids becomes equivalences between different braid words. And so one way to ask the question is, how do we determine when two words or sentences carry the same meaning? And this is, these questions are the domain of what's called natural language processing in knot theory, in machine learning.
I have a question.
Sure, yes.
So I was wondering if it's for untied the knots, it's only you can do operations one per time, or are you allowed to do 3 operations at the same time simultaneously?
What I would say is that you can view the operations in a sequence, and then you could imagine as a human doing them in that sequence, and then taking the amount of time between each step in the sequence to 0 so that they're all effectively at the same time. But crucially, order matters. So the order does matter in the sequence. So for example, right, these I and J commute if and only if the distance between I and J is above 1. So order matters. Sigma 1 and sigma 1, sigma 2, 1, 2 in this language is not equal to 2 times 1. So order does matter, but you can do a sequence of them very quickly as a human if you would like. A computer can do them even more quickly.
Okay, so the number of operations basically you can say that the complexity grows as a polynomial.
It depends on what you mean by complexity and what operation you're trying to achieve. I will have something to say about complexity later, but I'll probably leave it for now. Yeah.
Okay, thanks.
Anyone else? Okay. So this is natural language processing. So in the interest of time, I'll just give you one example. Natural language processing is very impressive. This is the state-of-the-art machine learning result in 2020. A neural network was trained. It was then fed this text, and the goal of the training procedure was to have the neural network learn how to complete sentences, paragraphs, stories, etc. So a human gave it a prompt that said, below is a screenplay for a film noir hard-boiled detective story by Raymond Chandler about the boy wizard Harry Potter by Raymond Chandler. And then the neural network wrote this English. Harry Potter, private eye, scene a small dingy office, early morning, furniture of the Salvation Army store variety. You're imagining that this could be a movie that's in black and white. And you can read on. There's not actually that much about witches and wizards in here, although there is a little. But this is pretty impressive that this text was generated by a neural network, just given this prompt up here. So this is the state-of-the-art result in natural language processing as of last year. In our context, we can imagine that natural language processing might learn commutativity. So for example, he's sometimes right and sometimes he's right as sentences. The words have been exchanged and the meaning is basically the same. On the other hand, the scientist eats the chicken and the chicken eats the scientists. We have changed the order of the words, but the meaning has changed drastically. So learning commutativity or non-commutativity is important. You can also learn various types of equivalences. So that's sort of the setup for why we might think of knots in terms of natural language. What I'd like to tell you about now is the unknot problem. And this is a simple to state but difficult to solve tangling problem. The unknot problem is the following. Question, is a given knot K the unknot? So in particular, if I hand you a knot that looks like this, I want to ask, can I deform it without ripping and tearing into this object? Or, in which case I would call it an unknot, or is it fundamentally knotted? This is the simplest knot that is non-trivial. This cannot be ever deformed into this one without ripping or tearing. Okay. One says that this is a knot, one says that this is the unknot. In terms of complexity, there are topological invariants of knots. What one would like is a knot for the unknot problem is a topological invariant that distinguishes the unknot. What that means is that for the unknot, that topological invariant has some particular value, and that a knot has that topological invariant value if and only if it's the unknot. It would be a way to distinguish the unknot. There is no easy to compute invariant that detects the unknot, for instance. So there's not some topological invariant that is fast to compute that it can definitively answer whether or not a knot is the unknot. On the other hand, you can say to yourself, fine, there's no topological invariant, but can I just screw it up with all of these different equivalences and try to untangle it myself and see whether or not it is non-trivial? So this is the unknot problem. I want to make the point about how this gets harder with the number of crossings by introducing you to Not or Not, a game for children. This paper was written in my first year of fatherhood last year, and I decided to write an appendix for my daughter to play with someday. And you can see that the knots over here are way more complicated than the knots over here. So I ask you to focus your attention on this one and ask, can you untangle this one without ripping or tearing? I'll put Kevin on the spot because I know Kevin. Kevin, what do you think? Can you untangle this one?
It looks untangleable.
Yes, you can untangle it. That's right. On the other hand, this one, you cannot. So by the power of Kevin, he stared at this and used the method of staring for 30 seconds, and he said, yes, you can untangle this. Now I will ask Kevin, okay, how about this one? Can you untangle this one?
Well, I have a 50% chance to say that it is.
Yeah, you do have a 50%
untangleable.
chance of, yeah, you have a 50% chance of guessing right. It so happens that I stacked the odds here that half of them on this screen are unknots and half of them are knots. So this is an unknot. There's a way to untangle this thing, but it's not obvious if I just hand you this. And this one cannot be unknotted, for instance. Okay. So the point is that it gets harder as the number of crossings goes up. From the point of view of complexity theory, one option would be to just try all possible moves, and that will take time that is exponential in the number of crossings. I won't go into complexity theory too much. It's too much of an aside from the point of view of this talk. But I will point out that there is no known polynomial time algorithm for solving the unknot problem. There may be one, but we don't know of one. And by that, I mean polynomial time algorithm in the number of crossings.
Sorry, that Shor 94 is the Shor algorithm, the quantum Shor algorithm? Or?
Yeah, I'm just making an analogy. So I'm talking about the complexity of this problem in regard to other famous algorithms. So there's this, yeah, that's right. So this is Shor's famous paper.
Yeah.
So for example, for factorizing integers. So if I hand you an integer, factorizing it is very, very hard. Yeah, this is what Shor's algorithm is about. But there's a related question, which is easier, which is given an integer, is it prime or not, right? And it was only that's an obvious problem to ask about any integer. But It was not known that there is a polynomial time classical algorithm until 2002. So this was a case of where there was a problem that seemed like it was non-trivial, and I actually don't know the scaling complexity in the polynomial class, but it does happen to be true that this problem is in P.
Thanks.
And my point is, this unknot problem, we don't know whether it is in P or not. It could be that someone comes up with something clever at some point, but we don't know yet. So I will very briefly mention the decision problem aspect of this and a natural language technique that we used. I want to focus more on the reinforcement learning though, because I think that's more interesting. So this is a slide that just shows you that we have algorithms to generate knots and unknots that are complicated of some length. So to be able to ask these questions about whether or not you can knot something or unknot something, you have to have examples to play with. This is how we do it. This slide maps those knots and unknots, those knots that we generate onto a well-known set of knots, but this also isn't important for us here. There's a particular neural network architecture, which I won't try to explain except to say that it is very good for natural language. This will give you a sense of scale in the field. This is a very famous paper due to Vaswani et al. From 2017. The two most cited papers in my field, theoretical high energy physics, ever, have order 15,000 citations. One of them is from 1967, another is from 1996. This paper, I believe, is already over 20,000 citations since 2017. So this field is growing rapidly, and it is already orders of magnitude larger than my own. This is a very famous architecture called So there are two basic results that I want to show you here. One is that we are training a neural network on a standard neural network architecture. And then we're also training it using one of these natural language processing architectures, something called a reformer that is related to this attention mechanism. And what you can see, we're trying to ask the neural network, given a braid, is it the unknot or not, right? So I'm just trying to do something very simple. Answer a yes/no question. Is this braid, is the associated knot closure the unknot or not, right? What you see is that even very simple neural networks are already getting above 95% accuracy, right? So this is an example of how neural networks are pretty powerful. It's not perfect accuracy, but it is getting the right answer on data that it hasn't seen yet over 95% of the time. And you will also see that using the principled architecture that takes into account the language-like structure, it does a little bit better. For harder problems, you would expect the gap between the principled architecture that uses natural language and the brute force sort of dumb architecture to be bigger. But what this is telling you is that this is sort of an easy problem because the simplest neural networks you could write down that have been around for decades just do very well on this problem. Perhaps a punchline is that you may think that your problem's hard, but it only takes an hour to throw a simple neural network at relatively simple data problems. You should do it because it may be that you put a lot of time into coming up with what is the best approach when the simplest approach actually already does very, very well. But the other thing that I want to point out is that this neural network is, when it sees a braid, it labels it as one, or sorry, if what I should say is the value that it's trained on, if it is an unknot, is 1. The value that it's trained on, if it is a knot, is 0. And so the neural network is trying to map the input to some value between 0 and 1. And so for a knot that it maps to some number very, very close to 0, it's rather confident that it is a knot. For a knot that is very, at like 0.4, it says that it's a knot, but it's not that confident about it. And what I want to point out is that there's a clear decreasing trend here. If you take the output of the neural network, indeed, this is 10 to the 0 here, because this is a log scale, is really 10 to the 0. So indeed, the unknots are labeled up here, but you can see that there's a range of values that the knots are labeled with, from sort of 10 to the minus 10 down to 10 to the minus 18 or something like that. All of them are pretty close to 0. But when you take another axis here, which is the degree of an invariant called the Jones polynomial, you see that there's a clear correlation between the confidence that the neural network has in making its prediction and the degree of this Jones polynomial. It learns something about the topology of the knot. There's a correlation here, even though the training process didn't involve the Jones polynomial at all. So this is an interesting thing to point out because it seems that the network is learning something about topology implicitly. But what I want to focus my time on is reinforcement. And instead, I want to ask, can reinforcement learning find the sequence of moves that unknots the knot? So reinforcement learning is the following. An agent interacts in an environment. It perceives a state from state space. Its policy picks an action given the state. It arrives in a new state and receives a reward, and successive rewards accumulate via this sum into something that's called the return. Future rewards are penalized by a discount. So reinforcement learning requires developing a notion of value and certain approaches to it. The value of being in a given state is the expected, think of this return as sort of rewards averaged over time as an agent plays out some trajectory through state space, as it plays some game. If you do many, many, many trajectories, what the value of the state is the expectation value of the return given the state. Okay. And there's something called the action value function also that I won't get into. So this is the idea. So the agent starts its life out dumb, and over time, this policy function is updated so that it makes smarter actions. So it takes in a state, and over time, it learns how to take more intelligent actions. A famous example is AlphaZero. It dominates in chess. There is an interesting anecdote here. So this is showing that it can learn openings that have been played by humans. This is one called the Caro-Kann opening. And in the first 2 hours of training, the network almost never really plays this opening. And then for a while, for like almost 4 hours, it plays this about 10% of the time, and then it stops playing it. This is showing how the network is learning to change its opening strategy over time as it plays chess more and more. And incidentally, if you made this, you would see a similar feature of a bump in actual grandmaster play of this opening, because it was something that was very popular in the 70s, but isn't really played by top grandmasters today because they have better ideas. So there's this interesting corollary. One thing that is worth noting here is that these AIs that have world-class gameplay do not train on human data at all. It is just told the rules, and the algorithms associated with reinforcement learning cause it to become a world-class machine on the time scale of 8 hours of training. So there's a way to set up this unknotting game in the context of reinforcement learning. Remember, in reinforcement learning, I need a notion of state. So there needs to be a state space. The state is the braid, these braids that I showed you. There's an action space. The action space are topological equivalences of the knot associated to the braid. So there are moves that you can do to the braid that don't change the topology of the knot. We give it a reward that is the negative braid length. What that means is that the agent is incentivized to try to get shorter and shorter and shorter braid lengths. This reward is the thing that biases it towards trying to find unknots, because it tries to find something with braid length 0. And there's various algorithms for doing this. And we tried a couple of different things. The first thing that we did was try a random walker. You need some control set in science to compare to, right? The random walker says, given this state space and action space, the policy for all times will simply be to draw actions from a uniform distribution on action space. Literally take a random action, all actions weighted equally for all states. That random walker, you can see that as the braid gets longer and longer and longer, the accuracy is the percentage of the time that it's able to actually unknot it. it just goes down pretty rapidly with increasing n. On the other hand, there's a reinforcement learning algorithm called A3C that we use that does significantly better. Then there's another one called TRPO, Trust Region Policy Optimization, that does, I would say, very well. And there are ways to interpret what's happening here. And the way that that is done is via rollout. In the interest of time, that's sort of all I wanted to say about knots. I want to be able to tell you a little bit about quantum field theory because Kevin mentioned that might be of interest. But the conclusion of this section is to say that it's natural to use natural language processing techniques for knot theory. There's this unknot decision problem that I mentioned, but really my focus was on what's called reinforcement learning here. The agent learns to alter its behavior, for example, as in AlphaZero. And what we find is that the reinforcement learning agent, that the AI that trains itself to unknot these braids, does so much, much, much better than a random walker would. So this is the result, if you would like, that even with increasing n, it is able to successfully unknot the braid over 80% of the time. So that's this section. Are there any questions?
In YouTube, there is no question so far, but might take a couple of seconds to catch up.
Yeah.
In the meantime, I have a question. If you can elaborate a bit more about how you can, I mean, because you said that you can do this with the chess. So how you implement like the different restrictions of how the pieces can move in a neural network? Do the algorithm change somehow the number of nodes for this or in your network?
Yeah. So the encoding of the details of the state space is something that is sort of done on the human side. What the neural network is doing, the neural network is this policy function here, pi, yes, that takes a state and gives an action. So all it needs to do is presented with a state, like a particular chess position. It needs to know, in the context of chess, you have to have a way to encode all possible actions, right? And that's something that the people at DeepMind figured out. It's the same thing that you would normally do in a normal chess game, right? For a conventional chess computer program, the computer has to know what all possible actions are. So you just even could take that library of all possible actions. The crucial thing that the neural network is doing is giving you a function from states to actions. Really, this is a state-dependent probability distribution on the possible actions. So that's the context. So you need an encoding of the action space, but this is doable because chess programs have been doing this forever. In my context, the actions are the different types of moves that you can do to the knot.
And the algorithm doesn't change the set of actions, right? This is constant, fixed.
Conventional reinforcement learning has a constant state space and a constant action space, so that as the agent explores the state space, it can learn to change how it acts.
Right. Okay. Thank you.
Anyone else?
I think we can move on. Like probably YouTube already catch up.
If there are more questions on knots later, I'm happy to take them. The other is trying to use physics. Okay, so this example, I'm trying to convince you there's this triangle where math, physics, and computer science all belong together, and any edge of the triangle might be an arrow directed from one to the other where one field can influence another. This is the physics 2ML edge. And this is based on a paper that we wrote last year and another one this spring called Neural Networks and Quantum Field Theory. I'm going to pass through the learning slide in the interest of time. This is a way to understand learning in this context. I really want to get to the basic point of the talk, of this part of the talk. I love this slide, but it takes a minute or two to explain. So, very good. Okay, I'm through it. So what I want to do is try to convince you that neural networks are actually a lot like quantum field theory. So I'll need to explain the very basics of quantum field theory from a statistical point of view. And then I'll need to give you a correspondence between quantum field theory and neural networks, and I'll need to explain why they should be at all like each other in the first place. And I'll end there. So what is quantum field theory physically? What are Feynman diagrams when you put them in the simplest possible way? And what does this mean about statistics? So quantum field theory is a quantum theory of fields and their particle excitations. It's fundamental. It's for both fundamental particles, for instance, the Higgs boson, and also for quasi-particles, for instance, in superconductors. And a single quantum field theory predicts radioactive decay rates, the strength of particle scattering, etc. And there's two main perspectives: canonical quantization and Feynman's path integral. There are many Nobel Prizes in this area, and I'm happy to try to name them. But perhaps one way to say the basic idea, or one of the basic ideas that arises, is based on the Higgs boson discovery from 2012, that the Higgs boson is produced at LHC, here it is H, and it can travel along and decay via a loop of top quarks into two photons, and this is a Feynman diagram. This interaction, from a statistical point of view, is really this interaction and this interaction and this interaction all correspond to non-Gaussianities associated with the standard model of particle physics. Interactions are non-Gaussianities, right? I'll have more to say about that. So if this Feynman diagram is describing this decay process of the Higgs to two particles, I want to get into the origin of Feynman diagrams. And to explain it to you in the simplest possible way, these are pictures for computing moments of Gaussian or near Gaussian distributions. The 2nth moment of a single variable Gaussian distribution is of this form. It's a ratio of integrals, and you can compute these integrals, and what you get is 1 over a to the n, 2n minus 1 double factorial. There's a basic fact about this combinatoric factor, 2n minus 1 double factorial, is that 2n minus 1 double factorial is the number of ways to connect 2n points in pairs. So already, this combinatoric factor, I just gave you a pictorial description of it via connecting points in pairs. And this 1 over a to the n, a basic fact of connecting 2n points in pairs, is that if you connect 2n points in pairs, you have n lines. So it seems like there should be a 1 over a associated with each line after you connect the 2n points in pairs. I just gave you a way to compute this expression using pictures, at least in language. So let's do it in a concrete example. This is x to the 4, the expectation value of x to the 4. So the number of ways of connecting 4 points in pairs. And you can see that these are 4 points connected in pairs in all possible ways. And for each one of them, for each line, I write a 1 over a, and then I sum over all possible ways of connecting them, and I get 3 over a squared, which is the right result. So Feynman rules are a picture to expression dictionary, and it gives you a way to use pictures to compute expressions. But I can do better than that. You could say, what if I don't have a Gaussian distribution? What if I have a distribution that's close to Gaussian? Here's my Gaussian. In the limit that this lambda goes to 0, it becomes the Gaussian. But as long as this lambda is non-zero, this is a non-Gaussian distribution. So what I can do is multiply by 1. And I'm also doing a Taylor series expansion in small lambda here. And what I can do is recognize that this ratio over this ratio is just the ratio of the 2n plus 4kth moment in the Gaussian distribution to the 4kth moment in the Gaussian distribution, summed over k and over these interactions. But basically what this is saying is that I can use perturbation theory to compute the non-Gaussian moments in terms of Gaussian moments, but the Gaussian moments have an expression in terms of Feynman diagrams. So this is a way to compute non-Gaussian moments perturbatively in terms of Feynman diagrams. So this is the statistical origin of Feynman diagrams. So it sounds like quantum field theory is physics widgets on top of a statistics backbone, and I think that's an accurate characterization. And so I'd like to ask, what is QFT statistically? Well, it's defined by a distribution on field space, the so-called Feynman path integral. The log probability S of phi is called an action. And what we do is we have measurements to, we do experiments to measure the correlation functions, they're called, and also the amplitudes of these quantum fields. So phi itself is a function of spacetime. There's a density, a distribution on these functions that weights it according to its action. And the correlation function, this Gn, is just an expectation value of a product of the functions weighted by the probability. Okay. So a free quantum field theory is one in which this action S, really this whole probability distribution, is Gaussian. There are no interactions in that theory. But perturbative quantum field theory, when they start interacting with each other, corresponds to non-Gaussian actions. And those non-Gaussian actions, you can compute perturbatively, and you can have Feynman diagrams to compute the moments of that non-Gaussian action, of that non-Gaussian distribution, just like I mentioned here. Okay. So that's the statistics of quantum field theory. But what does this have to do with neural networks at all? Well, that's really what I want to try to explain. So first of all, I need to define an asymptotic neural network. So a neural network is a function with a discrete hyperparameter n that enters into its architecture. Here is n. There's an asymptotic limit in which n goes to infinity. And the crucial property that I'm going to require is that as that parameter n goes to infinity, I want the neural network to be adding an infinite number of parameters, which themselves are random variables. You'll see why in a second. So an example that I'll give an equation for in a second is what's called a fully connected network. You may have seen a picture like this before. This is some complicated function where these different lines represent linear transformations between the values at these different nodes, but you could just write down a recursive complicated function for this. This direction is called the depth. This direction is called the width. And for me, the width is going to be n, and I want to take n to infinity. So the simplest example of this is what's called a single layer network. A single layer feed forward network can be described by an equation of this form. From the perspective of maps, it's a map from R to some input dimension, a map in this space, R to the dn, via these parameters, W0 and B0. W0 is a matrix and B0 is a vector. This maps it into Rn. There's an element-wise nonlinearity, sigma, that keeps it in Rn. And then I'm going to have some other linear transformation, some affine transformation that maps it to R to the D out. This is the function. It takes x, a vector x, it multiplies it by a matrix W0. That W0 matrix has its parameters drawn from some distribution. And then it adds a random vector. It acts with a nonlinearity. It multiplies it by another random matrix, and it adds another random vector. This is a single layer neural network. The limit of interest is the infinite width limit, where n goes to infinity. Then the output adds an infinite number of IID entries, independently and identically distributed entries from a W1 matrix. The central limit theorem applies, and so the output is drawn from a Gaussian distribution. Put differently, the language is that the neural network F is drawn from a Gaussian process, that is a Gaussian function space distribution. Let me put it yet another way. Neural networks, when you fire them up on your computer, are random functions. And just like how it doesn't make sense to ask, like, why did I get, if I have a dice, is there any fundamental significance to 6 when you roll a 6? No, that is a single draw from the distribution that is a uniform distribution on 1 through 6. The neural network is a single draw, a single random function from some function space distribution. And the claim of the machine learning literature is that this is a Gaussian distribution. The reason, more generally, to put this very concretely, if anywhere in a neural network architecture it adds n IID random variables, the sum is drawn from a Gaussian distribution. And so any time that happens in a neural network, the neural network is drawn from a Gaussian process at infinite n by the central limit theorem. This is the deep correspondence. I'm sorry, I'll make the key point in a second. I want to keep belaboring the point that all it's using is the central limit theorem And therefore, because the central limit theorem is pretty easy to make arise in a neural network by constructing the function in different ways, it means that many neural network architectures might have an n goes to infinity limit in which the network is drawn from a Gaussian process. And this is a long list of literature saying that there's lots of architectures that do this. And furthermore, this property is preserved under appropriate types of neural network training. The key point of this correspondence that we got interested in is to point out, as I already did, that free quantum field theory, non-interacting quantum field theory, is a Gaussian process. And therefore, one might imagine that one might take the techniques we know from free quantum field theory and apply them to neural networks that are drawn from Gaussian processes. But even better than that, I'm out of time, so I kind of want to make the main point. Yeah, good. So I made this point. The real question is, what about networks at finite n? These networks have a limit n goes to infinity, where the neural networks are drawn from a Gaussian process, a Gaussian distribution on function space. But what about at finite n? The basic point is that finite n networks, any non-Gaussianity in the density over functions associated with the architecture has to go to 0 as n goes to infinity, because it has to become a Gaussian process when n goes to infinity. And therefore, having a large neural network that is not infinitely wide, but has a very, very large width, corresponds to turning on small non-Gaussianities in the action that you could treat using techniques from quantum field theory. And that's the basic thing that we do in this formalism that we've developed. It's to say that neural networks are not fundamental themselves. The thing that is fundamental about them, since they are random functions, is the distribution that they are drawn from. But quantum field theory is all about distributions of random functions. And in particular, the quantum field theories we know best are about distributions of random functions that are close to Gaussian, which is also what neural networks are. So this sets up a way to map techniques from one field to the other, and this is a subject of a lot of my research currently. But I have a lot more material here. As you can see, I talk about renormalization, and I give you some experimental results and so on and so forth. But I don't have time for that. So I just want to summarize this basic idea that I tried to get across in the last 10 minutes, is that neural networks are random functions. They are drawn from some distribution. That distribution in some large n limit with a great degree of generality will be close to Gaussian. So these neural networks are random functions that are drawn from a close to Gaussian distribution, but that is exactly the framework of perturbative quantum field theory as we teach it, as I teach it in courses, as everyone teaches it in courses. So there is a deep connection between neural networks and quantum field theory. I think this will be one of the keys to an improved understanding of deep learning, because it's not the individual neural networks that are crucial, it is the ensemble, they can be crucial in the sense that they're very useful, but the fundamental thing about a neural network is not a particular random neural network that is drawn, it is about the distribution from which it is drawn, and that's the point. I have all sorts of other things to say, but I would rather conclude and talk to you. The overarching conclusions is that machine learning for math, I tried to convince you that machine learning is useful for math, in particular, trying to unknot knots in knot theory. And trying to apply physics to machine learning, I told you that neural networks are drawn from near Gaussian distributions, but near Gaussian distributions are the backbone of perturbative quantum field theory. So we could talk about directly importing techniques from quantum field theory to neural networks. So I think this is what's going to happen in the coming decades and years. This connection has been around for millennia. Computer science is a baby compared to math and physics, and that is exciting because it means there's a lot to do. I tried to give you an example here of where computer science affects mathematics in knot theory, this side of the arrow, and I tried to give you an example where physics affects computer science and gives us a new way to think about neural networks in terms of quantum field theory. But I think that really this is going to be a whole thing. It's already starting to be a whole thing. Our computer science techniques for math and physics are getting more and more sophisticated, and there's a lot of cross-roughing going on, and it's very exciting. So thanks a lot. Sorry to go a minute or two over planned, but I'm happy to take questions, and it's much more fun to talk with you than to talk at you. So please ask. So we can talk about whatever you want.
Okay. Well, thanks, Jim. This was a very fascinating talk. I would say that it obviously poses a connection that is not obvious between different fields, even though they look alike. And sometimes one might think that they are connected, like having them displayed in front of you is just fascinating. I hope for the attendance of the bootcamp that they were learning a little bit about machine learning and how all these processes are useful in many problems, that they can actually see that they're actually even more ingrained in more abstract and more fundamental problems in our understanding of the nature that surrounds us. So I would like to open the floor for any questions that the audience might have. Which they seem to be a little bit shy.
That's fine.
Okay. So I like somebody like I think it's Elkin said like Wolfram. I mean, like probably he's talking about Wolfram Alpha, I would say. Has talked, or maybe the same Wolfram. Has talked many times before about the relationship between computer science and physics. Any comments?
I think he's been thinking about this sort of thing for a while. A lot of people have. I'm not familiar enough with Wolfram's comments in particular to comment on his comments, so I better not guess. Yeah.
Okay, so we have another question by Lawrence that says, could machine learning be used to study the compound formation process in the area of material sciences?
Yeah, that's a great question. It depends on what aspect you're interested in. I think you're actually talking about the assembly. I don't know enough about that process, but it is true that people are working on these sorts of things. Two things that maybe are worth talking about in a little more detail is that I know people are using these for quantum chemistry. And in particular, one wants to take the symmetries that arise in quantum chemistry and sort of bake that into the neural network architecture. And people are doing that there. Of course, quantum chemistry is related to material science, but at a smaller atomistic and molecule level. I also just hosted a talk at noon, which you'll be able to see on YouTube later in this Physics Meets ML that I advertised on slide 2. And that talk was about using a modern library called JAX for molecular dynamics simulations. And one of the things that it showed is how you can use JAX and machine learning to model various glasses that are arising in molecular dynamics. So these sorts of things are absolutely used in material science. It's just that I'm not as familiar with those applications.
Okay, maybe we'll give a few more seconds to see if any questions pop out.
Yes, hello. I have a question. Is it necessary for most of research in computer science in general, use powerful machines?
That is a good question. I should start with saying that I'm not a computer scientist, so I will tell you my best physics understanding of the answer to that question. Sometimes for sure. So if your computer science research is experimentally driven in the sense of computer science experiments, those experiments can quickly require supercomputers and of various varieties, and in particular, GPUs and TPUs and things like that. Even for my own desktop that I am currently on, I have what would be considered a very powerful desktop. I have an AMD Threadripper with 24 cores and 48 threads on there for the CPU, and my GPU, if you're gamers, is an RTX 3090. I just got it, and that's for my local needs here on this computer. Generally, one needs, if one wants to do state-of-the-art experiments, one needs very strong computers. One of the avenues in machine learning is, of course, how to better understand it so that you don't need such intense levels of resources. And then furthermore, in computer science, there are some questions that are fundamentally theoretical that don't require even running any code. For example, the complexity of certain problems in graph theory is technically an area of theoretical computer science or discrete mathematics. And that's a very famous subject that is relevant, for instance, for how Google Maps will route your car through your road trip or something like that. So those are questions that don't require, in principle, any computers at all, unless you want to do experiments. But you could imagine turning certain computer science questions ultimately into a math problem that you can do on that blackboard or something like it. So, but the answer is state-of-the-art experimental aspects of computer science that require running big codes, of course, require big computers. So.
Okay, I think we run out of time. So first, I would like to thank Jim for this nice talk. I hope everybody had like a nice time and learned a little bit about what's been done in the state of the art and knowledge on physics and computer science and math, of course. Again, like I know, Jim, maybe if you have any close remarks to to invite people to maybe contact you if they have any other questions, then you can do it. Otherwise, yes. I'll just sign off just by saying thank you to everybody to be here, for being here. And I hope we see you again sometime soon. So go on, Jim.
Thank you very much. It was good to meet you all. Feel free to get in touch. If you're interested in this area of the intersection of physics and machine learning, I can go back many slides all the way to the beginning. And I will point out that checking out this website associated with our wonderful NSF Institute, or checking out this website, which is related to this seminar series I help run, are great places to start. And if you want to send me an email, feel free. It's the beginning of the semester, so I might take a little while to respond, but feel free to. So thank you very much, and good luck with the rest of the boot camp.
Okay, thanks, Jim.
Yeah, thank you.
Well, okay, thanks everybody for coming.
Bye.
We'll see you again sometime soon.
See you.
Bye, guys.
Thank you.